So, all right, the microphone is on? Okay, great. Okay, so before I start on the slides, let me just say a few words. I'm grateful, I'm sure we're all grateful to the organizers for this amazing conference. I'm grateful to the wonderful staff of the Princeton Math Department for making it run so smoothly. And I want to express publicly what Sergiu knows privately, my tremendous admiration for his very profound and important work. Okay, now this is the last talk of the conference. Bags are packed. We are tired. This is going to be an easy talk. It is expository. It demands no special knowledge. The experts not only know all the theorems that I'm going to say, but have heard me give exactly this lecture at least once. The new development is further research into the main joke. All right. The theme of the talk is the following. There are plenty of interesting equations that govern the motion of fluids, and many of these equations are rigorously known to lead to singularities in finite time. But those equations apply to compressible fluids. Incompressible fluids are evil, and it is very hard to prove the existence of breakdown in finite time. To my knowledge, until a few years ago, there were no known equations from physics textbooks from which singularity was rigorously known to form in finite time. And by a great stroke of luck, my Spanish friends and I discovered a few years ago 2 such examples. So I'd like to talk about those and about a third equation which we still don't, well, for which breakdown is still not known, although they're suggestive numerics. Okay, now let me see if I can remember how to operate. Oh, perhaps I don't have to. I have this. Okay, so I'm going to discuss 3 problems about incompressible fluids, and these are fluids with boundaries or interfaces, okay? And the singularities will form in the interfaces. So the equations are the water wave equation, the Muskat equation, I'll describe what they are, and alpha patches. Okay. And so, well, all right. Let me first give some credit. The distribution of credit in this talk is not perfect, but at least I hope I've gotten the teams of my own coworkers right. So here's the team for the water wave equation. Here's the team for the Muskat equation. And here is the team for alpha patches. Please notice I'm not a member of this team, I'm just talking about it. Okay, and here are the relevant papers. There is a reason why I'm putting the titles up. Okay, and the point is that in this talk, I'm going to explain intuitive ideas, but I won't even state the theorems correctly. I'll give an approximate indication of what the theorems say. But I promise you that there are actual theorems that say what I describe in this talk, and the detailed statements and the proofs of the theorems can be found in those papers. In this talk, if there is time, I'm going to sketch the ideas in the proof of the breakdown of the interface for the Muskat equation, one of the 3 problems. On the other hand, bags are packed, and if it comes to a contest between getting through all the material and finishing on time, I will come down on the side of finishing on time. Okay. Okay, so let's start with the water wave problem. Now there are serious experts in the audience. Well, all right, they know everything I'm going to say. Never mind. So let me describe the water wave equation in 2 dimensions. So we have air or a vacuum or something on top of a water wave, and then underneath this curve that you see on the slide is the water region. The boundary between the vacuum and the water region is the interface. So the water region is called omega of t. T is time. Gravity is acting on the water, but it doesn't do very much to the vacuum. In the water region, there is a velocity. So u of xt is the velocity at position x and time t, and there is a pressure, p of xt. The velocity and the pressure, so of course the velocity is in R2 because this is a 2-dimensional problem and velocity is a vector. The pressure is a scalar, but these are only defined when x is in the water region, omega of t, and we don't know what omega of t is. We have to solve for that as part of the problem. Okay, so let's mathematically represent the interface, the boundary of omega of t. Let's represent it as a parametrized curve. So t is time here, and alpha is the parameter of the interface at time t. And the parametrization has no physical meaning. We can pick our own convenient parametrization, but if we change from one parametrization to another, that has no effect on what the water is unaware of that and doesn't care. Okay, what equations are satisfied? Well, there is, first of all, the 2D incompressible irrotational Euler equations in the water. So in omega of t, F equals ma, and so we have the first equation, which I'm sure you recognize, that's the 2D Euler equation. The fluid is incompressible, so the divergence of U is 0, and this flow of water is assumed to be irrotational, so the curl is 0. That's not necessary. Actual water is not irrotational. It can rotate for a variety of reasons, but the assumption that the curl is 0 is internally consistent. That is, if the initial conditions are irrotational and you let the thing evolve, it will continue to be irrotational. And so that's just the simplest case, and we have enough trouble with the simplest case. Okay, now that describes what's going on in the water region. Now there are boundary conditions. So at the interface, first of all, we can take the pressure to be 0. That neglects surface tension. I'll come back to that. We take the pressure to be 0, and furthermore, the interface moves with the fluid. So if you take one particular red dot take one molecule on the fluid interface, color it red, and see how it moves according to the velocity field. So you integrate a simple ODE, the velocity is given, etc. The red dot stays on the interface. So molecules on the interface move with the fluid and stay in the interface. And so there's the equation written on the slide. Notice that there is some function c of alpha t, which can be arbitrary, and the arbitrariness of c of alpha t reflects the arbitrariness of the parametrization of the curve. So changing the c doesn't really affect the solution, but we may want to pick a convenient c for our own purposes. Okay? All right, so this model takes pressure and gravity into account but neglects surface tension, although the results that I'm about to describe hold also when one adds surface tension. So I'll say more about more sophisticated models. Okay, so those are the equations. We specify at time 0 the interface and the velocity. Of course, initially we want the velocity, we want the interface to be smooth and the velocity to be smooth, and if at all times the velocity is supposed to be irrotational and divergence free, well, that had better be true of the initial conditions in particular. So those are the restrictions on the initial conditions. We now have initial conditions, we have our equations, and we solve for time going forward, and we ask whether a singularity can form in finite time. And we will see the answer is yes, of course it can. Okay. All right, Here is a discussion of previous work. This discussion, so I will give some credit to some people, but this is by no means complete, and my apologies if you have done fundamental work on the problem and your name is not mentioned. A lot was known. Okay. Since the slide was written, I confess the slide is not current. There has been further work. We've been at the remarkable lecture of Alex Ionescu giving global existence for small initial data for the hardest form of, well, for a much harder form of the problem than I'm talking about now. Okay. Here are more people and more results. All of these results, one way or another, say that solutions of the water wave equation do exist. Either for short time there is no singularity and everything evolves in a nice smooth manner, or for small initial data, everything evolves nicely and stays smooth and even decays in a certain sense as time goes to infinity. But the results that I want to talk about now are going in the opposite direction, showing that a singularity can form. So here's what the singularity looks like, and the physical mechanism is completely obvious, and it's clear to intuition that it happens and that nothing can stop it, or, well, we'll see what might stop it. All right, here's the initial condition. The water is in gray. The region above the gray is the vacuum or the air or whatever. The initial U and the initial boundary are smooth, okay? Those are the initial conditions. Now, the water wave in B has turned over, so at some later time, the interface is no longer the graph of a function. It is a curve that looks like this picture. But nevertheless, U and the boundary, so the velocity field and the boundary are still smooth. Okay. On the other hand, they're headed rapidly for each other, and what is there to stop them? Nothing. And so at some point they collide, and we call that a splash. And so the interface at some critical later time self-intersects at a single point, but except for that, the velocity and the boundary are smooth. That's a singularity in the sense that there is no physically meaningful solution of the water wave equation beyond that time. I don't know what water will actually do under these circumstances, but it will not satisfy the water wave equation. Okay? So that's a splash. There is a variant of the splash called the splat, and in a splat, the curve self-intersects along an arc rather than along a single point. So that can happen too. And except for that self-intersection, again, the velocity and the boundary are smooth. All right, so now what can we prove and what do we believe and why do we believe it? We can rigorously prove, and it's actually not hard, that a water wave can start as in A and end up as in B. Remember, here's A, nothing unremarkable, and then B, it's turned over. So a water wave can start like that and then turn over. We can prove that, and it's easy. Less easy to prove is that the water wave can start as in B and then end up either as in C or as in C prime. Okay? But what we believe, based on a simulation, which I'll talk about in a minute, based on a simulation is in fact the water wave can start as in A, then turn over so that it looks like B, and then continue on until it looks like either C or C prime. That's a strictly stronger theorem. Now, that's based on a numerical simulation modified from a simulation of Bielhau and Lohengrab. And the point is that, fluid mechanics is filled with interesting simulations which have the remarkable property that just as things get interesting, you lose confidence that they are correct. But this simulation has the good property that if you do things like change the mesh size, or, I mean, it's very clear that the method here has been fixed so that it remains accurate up to the moment of singularity formation, and so we believe it. We're working to produce a rigorous computer-assisted proof. The computer-assisted proof would start with an approximate solution produced by the computer, and the computer would check a lot of properties of this approximate solution, and then there would be rigorous argument that if those properties are true, then nearby there's an exact solution that forms a splash. But that's a huge project, and it's far from finished. So it is, as they say, work in progress. Okay? Okay. I should mention that there's another, here's more credit. Coutan-Scholar gave another proof with applications to 3D water waves. Okay. Now, what can stop the splash? Well, real water has viscosity. If we throw viscosity into the problem, we get some, instead of the Euler equations, the Navier-Stokes equations, and instead of simply saying that the pressure is 0 on the boundary, there's some more complicated boundary condition discovered by Stokes. But it turns out, as the team ground out, it turns out that adding viscosity does not stop the splash. On the other hand, there's a theorem of Alex Ionescu and Victor Lee and me that says that a second fluid, an opposing fluid, stops the splash. As the splash starts to occur, the opposing fluid can push back, and so a splash does not form. But one has to be extremely careful about what that means. Remember, the definition of a splash, which I more or less gave, was that the curve self-intersects at a point, or perhaps at an arc, but is otherwise smooth. So perhaps at the moment of self-intersection, other stuff happens, like the curvature blows up or something like that. So in fact, what really happens with an opposing fluid is not so clear. I'm sorry?
What is an opposing fluid?
Oh, an opposing fluid, I'm sorry. Instead of water and a vacuum, there is water and another incompressible fluid. I'm sorry. Okay. Okay. Was anything else unclear? This is supposed to be completely easy and elementary. Okay. Okay, enough about water waves. Let's see, how am I doing? Okay, the Muskat problem. The Muskat problem describes two different physical systems. One is, let's say, oil and water in sand. So we have a porous medium, that's the sand, and we have two fluids. Described here as oil and water. They both live in the sand. This is a two-dimensional problem, so we imagine a two-dimensional world filled with sand, and maybe above the sand is some oil, and below the sand is some water, or maybe vice versa, and between them is an interface. Oil and water do not mix, they tell us. So, okay. Okay, there is a completely different physical system which is described by the exact same equations for reasons that I don't quite know, well, that I don't at all know. It is the Helly-Shaw cell. It consists of two parallel plates of water separated by a very thin gap, which is partially filled, well, which is filled with oil and water, as shown. This Helly-Shaw cell is vertical, as Peter pointed out to me in an earlier incarnation of this lecture. Helly-Shaw cells are usually horizontal, but they can also be vertical, and this is the one we're going to talk about today. So these systems are described by exactly the same equations. Now, what are those equations? So before I get to the next slide, I will tell the joke that I always tell when I give this lecture. It is from one of my favorite moments in literature. So in my reading of War and Peace, I'm sorry I don't speak Russian, I read an English translation. There's the following discussion toward the end. We must seek to understand the laws of history, which govern the affairs of mankind as surely as the physical world is governed by force equals mass times velocity. Okay. Now, I would like to. All right. So one could wonder: is this a feature? I mean, did Tolstoy really say that? What did he say? What did the translator add? I'm grateful to Andrei Okunkov and Svetlana Zhitomirskaya for researching this problem. In particular, Svetlana researched it in depth, and the executive summary is that Tolstoy is innocent, but there is a word in Russian which has multiple translations to English, and commentators and translators have since misunderstood. Okay. However, it happens that the translation of Tolstoy applies perfectly to the problem at hand, because F equals ma does not hold for this system. Well, what does that mean? Of course it does, but we don't want to take the sand into account. And so if we just think about the oil and water and not the sand, then the fluids are governed by Darcy's law, which is that the force is proportional to the velocity. And so there it is in the middle of the slide. There's the last term there is the force of gravity, which involves a density, and the density is different depending on whether you're in the oil or in the water. Okay, so of course omega oil of T is the region in the plane where the oil is, and omega water of T is the region in the plane where the water is, and they share a common boundary. That's the interface. Okay, so that's Darcy's law, an experimental fact. But by the way, Svetlana points out that Darcy slightly preceded Tolstoy. Okay. Okay, and so what happens?
Aristotle preceded Darcy.
I'm sorry?
Aristotle preceded Darcy, and Aristotle also.
Oh, really?
Forces. Yes.
Oh, he's master. Oh, of course. Oh, of course. Okay. 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 So it's Aristotle's law. Okay. Okay. All right. At the interface, here are the conditions. First of all, notice the pressures balance. Okay, they're equal. On the other hand, the velocities may differ, but the difference between the velocities is tangent to the interface. And if that were not true, very strange things would happen. Okay? And so there you see, at the bottom of the slide, you see two possible ways to express the fact that the interface moves with the fluid velocity. Which fluid velocity? It doesn't matter, because even though the two fluids have different velocities, the difference is tangential, and therefore doesn't affect what the fluid, I mean, how the interface moves. Okay, so we're neglecting surface tension here, and that's going to have very profound effects in a little while. And we restrict attention to the case in which the oil and the water have different densities, but the same viscosity. So, of course, that excludes actual oil and actual water, but I'll continue to refer to them as oil and water. Okay, we fix the conditions at time 0, and we seek a solution for times greater than 0. Now, it turns out that in this problem, it makes a crucial difference whether the heavier fluid is on top or underneath. So you see on the slide 3 scenarios. On your left, you'll see the light fluid on top of the heavy fluid. That's good. That's linearly stable, and at least locally or for small disturbances, nothing bad happens. In the center, you see the opposite. The heavier fluid, the water, is on top of the oil. That's very bad. If you try to solve the initial value problem with time flowing forward, it's highly unstable. Solutions typically don't exist. It's extremely bad, but that's because time is flowing forward. You should solve this bad problem for time flowing backward. You should start at time 0 and let time flow backward, and then you would find that this bad scenario suddenly becomes good. On the other hand, there is the really bad scenario, or I guess I should call it good, bad, and ugly. The ugly scenario is depicted on the right, on the far right. Yes, and on the far right, we find that sometimes locally the oil is on top of the water, but in other places the water is on top of the oil. And so if you try to let time flow forward, that's very bad, because somewhere the water is on top of the oil. But if you try to let time flow backward, that's very bad, because somewhere the oil is on top of the water, and you are just plain out of luck. Okay? The way to think of that is that the Muskat equation, in the good case, is a nonlinear version of something like the heat equation. So I've written the actual linearized Muskat equation on the slide. And so this is a one-dimensional version of something like the heat equation, except instead of the Laplacian, you take the square root of the Laplacian. So it's first order, morally first order. That's the good case. The bad case of Muskat is modeled by the two equations that you see there. You could change the minus sign to a plus sign, and then you would want time to flow backward, sort of as if you were solving the backwards heat equation. Again, it's not a heat equation. There's a square root of a Laplacian instead of a Laplacian. But still, there's a direction in which time wants to flow, depending on the sign in front of that lambda. But in the really bad case, the model that you should think about is this. I mean, our equation is some nonlinear version of the equation dtz equals sigma times lambda z, where sigma is a coefficient function that changes sign, so that you can't solve forward and you can't solve backward, and you're out of luck. All right. Now, there's previous work on Muskat, and again, I will give probably a credit to a Cantor set of the people who deserve it. So here are some of the people who have proven good things about the Muskat equation. We're going to prove bad things about the Muskat equation. So for small initial data, global smooth solutions exist. Let me mention that the smallness condition is rather, I mean, for smallness conditions, this smallness is quite big, okay? So if initially the interface is a graph whose tangent has slope strictly less than 1 everywhere, that's enough to declare that things are good in the stable case. And so, okay, but nevertheless, a singularity forms. And so here's the scenario, okay? We have, so we have initially something that looks perfectly innocent. We have oil on top of water, that's the good case, time is flowing forward. The interface is a graph, and we are in the good locally stable case. This problem is linearly stable. All right. However, the world is not linear, and here's what happens. The water turns over at some later time, so that its graph looks like that. All of a sudden now, we are in the ghastly case. Despite the fact that we're in the ghastly case, the solution does not instantly form a singularity. It continues for a little while for reasons that we'll see. But then at some time strictly after the turnover, we run out of luck, and the interface runs out of luck, and at a single point, it becomes singular. Singular means that it is C3 but not C4. You can ask yourself, does that imply that it's singular? Do you like that or not? One can convince oneself very easily that once that happens, there is no reasonable solution. I mean, there is no solution of the Muskat equation in any reasonable sense beyond that time, although that's not rigorously proven. So except for that, everything is swell, and all the interfaces in question are real analytic, except at the very last time at the 1 point.
So you cannot make it sense as a weak solution?
Up to the, you mean beyond the time? I mean, yeah, okay. I don't have a proof, so I can say anything I want, but I would be amazed if there's a weak solution. Okay. All right, so we have a rigorous proof that stuff actually happens. And let's see. I think there's enough time that I can actually present it. So let me go quickly through alpha patches. This is the problem of the three for which there are no rigorous results, so I will give it short shrift. Here, this is a two-dimensional problem. Again, we're in the plane. X is a point in the plane, and there is a region, omega of t, with a boundary, and the boundary is going to move. Okay, the blob is going to evolve, its boundary is going to evolve. And we are looking at an active scalar. Think of it as a temperature. And the temperature is equal to 1 in the blob and 0 outside the blob. Now, the blob is carried along by an incompressible fluid velocity. An incompressible fluid velocity in the plane is given as the perpendicular gradient of a stream function. So after the words incompressible fluid velocity, you see an equation that expresses u, the velocity, in terms of a scalar function, psi, and that is just the most elementary potential theory. It expresses the fact that the fluid is incompressible. But then the equations of motion in the box say two things. The first equation there says simply that the temperature is carried along by the fluid. And, well, remember, the temperature is 1 inside a blob and 0 outside the blob, so the blob is borne along by the fluid. And the second equation explains how the velocity arises from the temperature, or from the blob. And the story is that the stream function, which gives rise to the velocity, is equal to a power of the Laplacian applied to the temperature. So the first equation says that the blob is carried along by the velocity, and the second equation explains how the blob produces velocity. This alpha is a parameter, and well, I'm behind the times. Alpha these days is between 0 and 2, but I'm interested in alpha between 0 and 1. And two particularly interesting cases are alpha equals 0 and alpha equals 1. When alpha equals 0, this is the vortex patch problem for the 2D Euler problem. This is a famous result of Chemin with a simpler proof by Bertozzi and Constantine. The case alpha equals 1 is the analog of the vortex patch problem, but not for the 2D Euler equation, rather for the SQG equation, which models the evolution of temperature and wind on the surface of the Earth in response to the fact that the Earth turns on its axis. Okay, but we can fix a parameter alpha, we fix an initial smooth region, and we ask how it evolves, and can a singularity form in finite time? There's a result of Jose Rodrigo that says that the boundary stays smooth for a short time, but in terms of global information, we don't know. Numerical simulations suggest that the following thing can occur. Look at the picture on the left. That's supposed to be innocent and smooth at time 0, but at a later time, t1, the two tips have sharpened and approached each other, and at the moment of breakdown, the two tips coincide, the curvature becomes infinite, and we have a singularity in which emanating from the dot are 4 arcs. Okay, that's what appears to happen. Okay, and moreover, the singularity appears based on numerical evidence to be asymptotically self-similar. So that's one strange phenomenon. There's another mechanism also discovered more recently by Scott and Dritchell. Here's the reference, and I'd like to show you their amazing picture. So in the amazing picture, all right, now let me try to use for the first time the laser pointer. Whoop. Oh my God, what a disaster. There, let me try again to use the laser pointer. There it is. All right, see there, that's the picture. We have two little blobs separated by a little filament. But if you blow up the filament, it looks like this, and notice that there are these little waves. Now, this whole tan region, let's see, if you look at this whole let's see, do I have this backwards? No, I think so. Anyway, if you blow this, in this region, look at this little green square. If you blow up that little green square, you get this is what you get, and it looks, I mean, it has these same wiggles. And sitting inside there is the purple square, and if you blow that up, you get this, and it seems to have similar wiggles. And there's a little square of whatever color that is, very light blue. And if you blow that up, it looks like this. And if you blow that up, it looks like this. And if you blow that up, it looks like this. And if you blow that up, it looks like this. And so think of the numerical simulation with enough precision to produce that. So this is an interesting thing which is not at all understood rigorously. Okay, now I'd like to sketch the proof of something. Again, I will prove nothing. I haven't even precisely stated anything. But I would like to sketch the ideas in the proof of the formation of the singularity in the Muskat equation. Okay, so here's an oversimplified sketch of the proof, and the plan is that it will take about 10 minutes and then we'll be done. Okay, so, so here are the main steps. First, although the problem was originally formulated in terms of what happens in the oil region and what happens in the water region and what happens at the boundary, in fact, you can just get rid of unnecessary complication and write down a contour equation, an evolution equation for a contour. And so the claim is that that contour develops a singularity in finite time. Okay, now in order to do that, the first thing we do is find a real analytic solution to the Muskat equation that turns over. Once we do that, we pick the correct norm. And remember, let's say from Alex's talk, how important it is to pick the correct norm. Once we've picked the correct norm, we then take our real analytic turnover solution, Z0, and we perturb it slightly in that norm. And that will produce a Muskat solution that turns over and breaks down. Okay, so let's write down the contour equations. This has been known for a long time. The contour is again given by z of alpha t. T is time, alpha is the parameter along the contour. It's in the plane, so it has two components, z1 and z2. And this arises from a Muskat solution with maybe a clever choice of parameterization, if and only if it satisfies the following equation. So here's the equation we're solving. Okay. Well, there it is. Proof by elementary potential theory and integration by parts. Let me not comment further on exactly how to think about that equation, but there it is. That's the equation we're studying. All right. Now, how are we going to find a real analytic solution that turns over? Well, remember that our system is morally first order. So there is a version of the Cauchy-Kovalevsky theorem which applies, and it means that given any real analytic curve given any real analytic curve, there is a short time solution that remains analytic for a short time. Let's try to construct a turnover solution by looking at the moment of turnover. At the moment of turnover, the tangent has got to be vertical at one point, which we take to be the origin. So there in the slide it says we're given a real analytic curve with a vertical tangent at 1 point, 0. Okay, Cauchy-Kovalevsky gives us a solution for a short time, positive and negative. Okay? All right. Now, if we take our initial curve to be an odd function of alpha, then by staring at the equation, you quickly learn that the solution remains odd for all time, at least for all time for which the solution exists. So if it remains odd, that has the agreeable property that the origin remains on the curve. So the origin doesn't move. And the crucial question is to understand the angle called theta of t in this picture. So the angle between the tangent to the curve at the origin and the vertical. And I'm making conventions in which theta of t as shown in the picture is negative. Okay? All right. The crucial question is, what's the sign of the time derivative of theta at the origin? If that time derivative is positive, and we know that we have a vertical tangent at time 0, then the situation is as on the slide. On the left, with time slightly negative, theta will be slightly negative, because theta is increasing and it goes through 0. And then for time slightly positive, theta is positive, and so there's the picture. And that's a turnover. So if the if the derivative of theta with respect to t at t equals 0 is positive, then we get a turnover. If instead it's negative, then here's the picture. We start with theta positive, then theta becomes 0, so we have a vertical tangent, and then theta becomes negative, and so that means that we're in a case in which there was already a turnover to begin with, but it goes away, so that's bad. We're trying to construct a turnover. So, all right, what can we say about the sign of d theta by dt? A good thing about this question is that we can calculate d theta by dt by just plugging in the equations for the initial conditions. We don't need to know any deep properties of the solution. We look at the formula for d theta by dt, we plug in our initial condition z, and we ask, what's that? Does it have any particular sign? And the answer is no. I mean, what you get is a mess, but the mess has no particular sign, and if you make a favorable choice of z0, you can achieve any sign you want for the time derivative of theta at 0, and therefore we can achieve in particular a turnover. So what have we done? We have found a real analytic solution called z0. It satisfies the Muskat equation for a fixed time interval around 0, all right, minus t0 to plus t0. It has an analytic continuation to a strip in alpha space for each t between minus t0 and plus t0. That reflects the fact that the thing is real analytic. Okay. So now alpha can suddenly be complex, and moreover, the solution turns over at time 0. That's what we've achieved. Okay, now what are we going to do? So here's the plan. We're going to, first of all, to define the correct family of norms. Okay, so for each time between minus t0 and plus t0, there is going to be a norm, depending on time. We are then going to find a Muskat solution z of alpha t close to z0 of alpha t in these norms with the property, 3 exclamation points, the property that at time plus t0, z of alpha is c3 but not c4 at a single point alpha equals 0. And yet the solution is defined and satisfies Muskat for all times from minus t0 to plus t0. How are we going to do that? We're going to solve Muskat with time flowing backward, starting, so to speak, at time plus t0 and then proceeding to time minus t0. And we've got to keep our solution going, but we're going to achieve this condition about how z of alpha comma plus t0 looks. We're going to achieve that just by taking that to be the initial condition. Okay. Then the hard part is to show that the solution exists, and you could wonder if you have something real analytic, how can you perturb it a little bit? And well, this is maybe clear. In the right norm, you can take something real analytic and perturb it, and it won't be so smooth anymore. All right, it's very important to pick the correct norms. So to define the norms, we first produce a family of domains in the complex plane parametrized by time. These are called omega of t. Now, by bad planning, lots and lots of subsets of the plane in physical space have been called omega of t. This is different. Alpha is a parameter. The curve is z equals z of alpha t. Omega of t is a set of alphas. Okay, it's not a set of physical points. I'll have a slide in a minute to say just that. But each omega of t is an open set containing the real axis, or almost, well, at time t equals t0, the domain will pinch off to 0 thickness at one point. Here's the picture. Remember, time goes from minus t0 to plus t0. At the top, we have the earliest time, minus t0, and we have the domain there, which is fattest in the middle. Then at time 0, what is happening is that in some places the domain is getting thicker, but in other places it's starting to pinch off. And by the time we reach plus t0, the final time, the domain has pinched off to 0 thickness at the origin, and it looks as in the bottom figure. Okay. These domains have to be very carefully picked to reflect the behavior of the unperturbed Muskat solution. So you can thank me, I'm not going to explain that further. Okay, again, notice that our omega of t are sets of complex parameters, they're not sets of physical points. Okay. All right, so now what is the family of norms? Well, given a time, x of t is the space of continuous functions from the closure of omega of t to C2. Why to C2? Well, we have a curve z. It has two components, z1 of alpha t, z2 of alpha t. So we need two functions. We're most interested in how they behave for real alpha and t between minus t0 and plus t0, but they are defined and analytic for complex values of alpha in this time-varying domain. Okay, so f is analytic on the domain omega of t, and furthermore, when we restrict it, well, it's analytic and it's continuous up to the closure so that we can restrict it to the boundary, and when we restrict it to the boundary, it belongs to a suitable Sobolev space. H4 is good enough. Okay, 4 derivatives in L2 on the boundary. So that's our norm x of t. Okay? Now, all right, we want to use those norms to perturb the original Muskat solution. So we seek a Muskat solution z of alpha t defined for times between negative t0 and plus t0 with the conditions that you see there. First of all, z is close to z0 in the norm x of t for each t. Okay, z0 is our real analytic unperturbed solution, and we're now perturbing it in such a way that at time t, our solution is close to z0 in the norm x of t. And again, we are going to make an initial value problem, or should I say a final value problem. The z at time t0, the end of time, is prescribed, and we let time flow backwards to find the solution at other times. So it's not so obvious that this can be done at all, but it can be done because we can prove an energy estimate as shown, right? Anyone who has worked with PDEs knows that if you can prove an energy estimate, you're probably, well, if you can prove sometimes if you can prove an energy estimate, you are in good shape. I think with it, right, if conservation of energy were needed, then I think this conference would look very different anyway. Okay, all right. But in any event, there is an energy estimate. Notice the minus sign on the left reflecting the fact that time is flowing backward. And so this energy estimate is valid as long as the perturbed solution stays close to the unperturbed solution in x of t norm. And the proof of this energy estimate depends crucially on the relationship between the unperturbed Muskat solution and the family of domains. There is a term whose size one cannot control, but if you set up the family of domains correctly to reflect the behavior of the unperturbed Muskat solution, then the uncontrolled term, which is so big that it could ruin everything, has the sign that it helps you rather than hurting you, and so life is good. So, all right, and so the preceding can be done. And so, in particular, we can prescribe our initial condition at time plus t0 to be anything we want, provided it lies very close to z0 in this norm x of t0.